Hello. In this video, I want to demonstrate a program I've been working on for a while, which is a geometric constraint solver that can be used to draw simple figures. So I'll go ahead and boot up the program now. And this is the initial screen. So you can see the user has a grid here and then some controls on top. And I'll just demonstrate adding a point to the scene here. And as you'd expect, you can drag this point around the scene, move it around. So I'll grab another point. And the way that this program works is to draw shapes, you express the shapes in terms of constraints. So I can grab or select these 2 points here and then apply a horizontal constraint. And you can see what that's done is it's constrained these 2 points to be horizontal from one another. And I can add another point and add a vertical constraint. And now the program's worked out that these 3 points need to be in these 3 positions for these 2 points to be vertical and these 2 to be horizontal. But one cool aspect of this program is that you can drag a point and actually explore the space of all valid solutions with the constraints that you've set. So you can see that even though I'm just dragging this point, the top one, other points may move to satisfy all the constraints that I've specified. So to give you a better sense of how this program works, I'll make a quick example. So I'll grab a point here, and then I can use this lock constraint to hold it in place. Now if I try to grab the point, I can't move it. So I'll add another point, and this time I'll use a radial constraint. So I'll say this should be 75 units away. And now this point is constrained to be in a circle around the first point where the radius is 75 units. And to make this a little clearer, I can ink this a circle from where this point is the center and this point is the radius. And you can see that the point follows the circle all the way around. So maybe we'll make a little piston mechanism here, and the piston needs a base to rotate on. So I'll add another point here, and I'll use an offset constraint to keep this point exactly a certain distance to the right of my key point here. So I'll add an offset point, and I'll specify 300 units to the right and 0 units up and down. So now this point is locked in place, but just as a demonstration, if I remove this lock constraint, I can move the entire system, but this point and this point remain relatively locked to each other. So I'll go ahead and add that back. And now we need a point to move back and forth as the wheel rotates. So I'll place that point there and constrain it to always be horizontal with our point here. And now we can move this point along like this. And finally, I'll add an arm to attach the wheel to our sliding point with another radial constraint. And we'll say that should be 150 points, or 175, let's say. So to make this clearer, I can ink another line here and a line here. You can see now as I rotate our first point, we have a dynamic system here where the sliding point here adheres to the mechanical constraints that we would expect. So this program really allows you to create quite dynamic drawings because all of these solutions are valid, and we can just drag around to see which one suits us best. So now I'll close out of this and show how this program works behind the scenes. So fundamentally, at the core of the drawing program is a nonlinear equation solver. And the equation solver uses the gradient descent method. And to express all these constraints, we have here a simple language of expressions. And you can see we have variables, binary functions, functions that take just a single argument, and constants. And the benefit of expressing all of our functions in this way is that we can do symbolic manipulations on the system of equations as well as just purely numerical. So we also have an eval function here, which accepts a tree formed of all these different types here and spits out a value corresponding to the tree. So I'll jump over to our constraints here. And in this file, we record the actual functions that correspond to each of the constraints. And the constraint solver attempts to minimize each of these functions whenever it solves the system. So here we have our point constraint, and that corresponds with the lock. So if you add a point constraint, the point you've added it to is constrained to have its x equal to the input argument x here, and its y constrained to the input argument y. And we express this constraint in terms of two equations. The first equation just says that this node's x is equal to the constant x, and the second equation says that this node's y is equal to the constant y. And this being a gradient descent solver, we also record the derivative with respect to each non-constant variable in the equation. So you can see in each of these cases we have just one first derivative. This one with respect to x, and this one with respect to y. In more complicated examples, like our radial constraint, for instance, we have a function here which describes that all pairs of x and y must be a certain radius from the target, and we have four derivatives, each one with respect to one of the non-trivial variables. So to give a better indication of how the algorithm works, I've prepared a program called test_algo, which shows how we search the valid space of solutions once we've found a valid one. So you can see here that all this program does is make the blue circle follow my mouse cursor while being constrained to lie approximately on the black circle. And what this is actually doing is, behind the scenes, I've defined the expression for the circle, and the algorithm is finding points on the circle that minimize the distance from the blue circle to my cursor. And I also have a MATLAB program which shows that particular concept. So if I run this, we can see we have a similar or an identical situation here. We have a circle, and this set of points here shows 10 iterations of the solution traversing algorithm. So the red points here represent the initial value, and each of the blue points represent solutions that the algorithm tried but ended up rejecting, and the green circles represent solutions that the algorithm selected as being most optimal. And you can see that they overlap in the intermediary cases here because the algorithm uses the previous iteration as the starting point for the current iteration. So here we can trace the algorithm along from bottom to top, where we have our initial x. We tried all of these blue points, and the green one ended up being the closest to the mouse cursor. And we keep moving along, making sure that both our objective function is sufficiently minimized and that we're moving in the correct direction. So going back to our main program now, we can show this concept a little more clearly. So if I add a locked point there and add a simple radial constraint of maybe 100 units, we can see this is exactly the situation that we just saw in MATLAB, where the moving point is attempting to minimize the objective function, but also the secondary constraint on the point is that it attempt to move as close as possible to the mouse cursor. And if I add another point, we can see that in some cases, both conditions can be perfectly satisfied, meaning that we're within the objective function, there's a solution that perfectly matches, and the point I'm dragging, its location is exactly equal to the mouse cursor. But if I move out and move the cursor around like this, you can see that only one condition is satisfied, but the objective function always takes precedence. So we always ensure that the objective function is minimized, but we do a best effort approach when it comes to coming close to the mouse cursor. So that's all I want to show in this demo. Thank you for listening.